you don't miss anything. I'll upload this to YouTube later. Okie dokie, guys. So this is supposed to serve as a review of some of the terms that go along with experimentation, right? So as you look through Model 1, I really like these because they walk you through baby steps at a time through an experiment, right? So first question, what are some things that you saw that describe the reaction? Shannon, tell me something.
I said an Alka-Seltzer dissolved and it caused the water temperature to cool.
Okay, so it dissolved and then the temperature cooled down. Okay, cool down. All right, so I like that you mentioned the temperature cooling down. There's a term that goes along with that. So if a reaction's happening and the temperature goes up, well, what's reading it? Let's say instead of the thermometer being there, you had your hands wrapped around that beaker, and the temperature went up. What would that feel like to you? Okay, probably hot and warm. So would you say that's an endothermic reaction or an exothermic reaction? Exothermic, right? So if something gets hotter, the reaction itself is putting out energy to the surroundings. Well, guess what? Your hands are the surroundings. That's why you feel that, right? So if something gets hotter, it's called an exothermic reaction. RXN is reaction. Okay? So that's what that means. So using that logic, heat's being put out, that's exothermic. This reaction, is it exothermic? No. Be confident, right? You're right. It's not at all, because the temperature is not getting hotter, the temperature is getting colder. So now think about it. You're holding that beaker in your hands. What does it feel like to you? Right, so does it feel hotter or colder to you? It feels colder. The reason why is because as the reaction itself, which is inside the beaker, as it gets cooler, the reason why is because it's consuming energy. It's using energy. That means the energy is no longer there. And if the energy is no longer there, it just feels colder because it's just not there. So that would be considered an endothermic reaction because energy was taken into the beaker and used up, and that was no longer there. Those are two terms that we use, and they're hard to distinguish. But this is like Unit 5 in chemistry, so I just want to touch base with that, but not too much. All right, so we know that it's an endothermic reaction. What are some other things you see happening? What's this? Those are bubbles, right? Okay, fancy word for bubbles. Here we go. Oh, possibly. I can't remember what Alka-Seltzer is made of. I think it's like carbonate and acetic acid or something.
To be more general, it could be releasing any gas at all.
Right, it could be any gas, right? So the term bubble, the complex word for that is gas. And even better is there is gas evolution happening here. That is evidence of a chemical change, which I think is question 3. Okay, gas evolution, it means bubbles, and that's just a term that indicates that there's chemical change happening. So if we kind of did question 1 and 3 together, the other artifact or evidence of chemical reaction was the fact that the temperature changed and it got cooler. It's going to stay there. Okay, so that's kind of question 1 and 3 together. What are some things that stayed constant? Shout it out.
Volume.
Okay, so maybe the volume, but that's not, that we don't have a lot. Oh no, it says 100 mils of vinegar, so possibly. I'm looking for another one too.
The room.
Room pressure. So what's the room pressure units here? kPa, right? kPa means kilopascal. Kilo, K, is the general prefix for something that's 1,000 times bigger than base. Pascal is a guy's name who helped discover something about atmospheric pressure. So kilopascals was what that room temperature is noted as. All measurements must have a unit, and that's why you'll see milliliters, kilopascals, delta or degrees Celsius, stuff like that. Turn to Model 2. So questions 5 through 7. In terms of this data, you should be able to identify which of these trials. So all the vocabulary is peppered throughout here. Which trial represents Model 1? Trial 1. So all you had to do is match up the information from the first model to the next one. That's easy. So in terms of experimental variables, you have your independent variable and you have your dependent variable. Which one depends on the other one? Dependent depends on the independent. So this one is one that I can change. And so if you maybe heard before, I, V is the independent variable, and it's something or a variable that I can change. I have the power over an experiment. Well, what was the independent variable in this case? Lexi? The number of tablets, right. So the number of tablets controlled what, Christian? The number of tablets controlled what other variable?
The final temperature.
Right, the final temperature. So you could say the final temperature, or you could say like the temperature change, meaning how much it changed. So an easy way to write change is delta. Did anybody know that? Delta means change. Fun fact, easy way to write change. So the temperature change doesn't control the number of tablets. That just sounds silly, right? It's the number of tablets that controlled how much the temperature changed. So it's easy to rationalize if you kind of think about it. So in addition to independent variable and dependent variable, we have variables that remain constant throughout the entire experiment. We have a fancy name for them. They're called constants. Pretty easy. What are some constants throughout this experiment? Shout them out. Room, okay, so room pressure. What else? Initial temperature. And I heard one more. Volume of the vinegar. Okay. There's probably some other ones I didn't list here, but you can at least see the constants throughout the data table as well. So I think you guys gleaned some of the terms I want from that. Can we set this to the side? Okay. Nanotechnology. So I saw that a lot of you guys watched the video because I could see the views, and then also looked at the place where you had to put your topic and claim your topic. So I don't have everybody from what I saw midday today up yet, but I do know that there's some repeats. There's some things that were changed. So I'm going to go through and I'm going to make a third row or third column, and I'm going to say approved or not approved. And if it's approved, you're good to go. You can start looking at the phase 2 stuff, which is the public service announcement that tells the public why measurement's important and why it's important to your field. You can see those details in the same exact link. It's an active Google Doc, and I can continually clarify, because I had a number of questions last night, and you probably see that I clarified a little bit more, especially through Selly. Who got messages on Selly? Like 3 of them. Okay, so if you've not joined, or you have to make a login, and then search for CNHS Honors Chem, and then it'll prompt you to join it by the password, which is you guys are sweet. Okay, so just make sure you join that, because I do try to update you periodically. Thank you. Okay, so just make sure you're aware. You gotta be quick. Okay, so after that, I'll do the declined or accepted kind of prompt, and then you can look at the next part, but it's due September the 12th. So you got 2 weeks, so don't jump on that tonight. You got plenty of time. So the share thing where you're writing a reflection, that's going to be submitted to me in part 2. If you've already written a little reflection of what you researched, or you have a document, you started noting some things for yourself, hold on to that. I don't want it yet. It's a work in progress.
So this whole project was due September.
Yep, the whole thing's due September 12th. And we'll do a share-a-thon. So versus Joey coming up here, I want to share it with everybody about my project. We're going to do mini share sessions with people, so it's not so intimidating, because I know sometimes it's hard to speak in front of 35 people. I still get nervous sometimes, so it's okay. All right, does that answer all questions right now on nanotech? Okay. You guys are so talkative today. All right, so we're going to move to another activity. This stuff from yesterday, we don't need this right now. Okay, so for lab safety, generally we have to talk about why things are stored in a specific manner. So sometimes in a problem that you have to solve, sometimes you have to kind of take on a different persona so you can work with the goal that you need to work for. So what I have here is it's called the GRASP model, GRASP. So you can see your goal, your role, audience, situation, and product. We're going to finish this in class today to the best of our ability in small groups. So put on your new hat of a chemical safety officer. Okay, I see all your imaginary hats now, thank you. You're a chemical safety officer in a factory. And OSHA, who knows what OSHA is? 3 of us, okay, great. OSHA, they come and watch to see how I play with my chemicals and how I store them to make sure everything's safe, because there was many times where things are not stored safely. Who heard about the accident? I think it was at Northwest High School where the teacher did a demonstration and caught one of their students on fire with a pumpkin.
Seriously?
Yeah, last year.
How did you know the pumpkin?
I have a pumpkin demo. I'll do it for Halloween. But basically the ethanol kind of dribbled out onto the student's shirt So it was bad. There was one incident where it was really bad. Anyway, got your attention now, right? So chemical safety is pretty important, and making sure that things don't sit together that shouldn't sit together. Because sometimes cap kind of comes loose on chemical X, cap kind of comes loose on chemical Y. They start to mingle in the air, and maybe it could cause an explosion. Maybe it just causes some residue. Just depends. So OSHA's coming to inspect your factory to make sure that you are storing things safely. They're coming and you need to provide them with a chemical inventory. So what's in your chemical closet? And a diagram saying this is placed here and this is placed here, because these two things don't play well together. But these two can sit next to each other because they do play well together. They're not going to kind of react in the, spontaneously. So you're going to give them a diagram and a little explanation, not a presentation per se, but an explanation of why things are going to be placed where they are. So what I want from you is the product. The product is a diagram. That's mine. So I have to set an alarm to take attendance because I already got yelled at the first day of school. So I already did that. Diagram, I want to know a couple of things about why you place things where they are. Reactivity, you're going to be looking at the reactivity, and I'll show you where you'll find this information. You'll be looking at safety symbols on your chemicals that you're going to be placing in your safety cabinet. You're going to explain why things are located where they are, and if you can find this, like how long it's going to be stable, how long it can sit in there. Some things can sit in there for 10 years, where some things have to they're kind of going to expire in 6 months. So if it says stability or stable, then it's going to be fine. It's like good for 1+ years. I'm just going to kind of make that really general. That's the one you may not find readily. So what you're going to see when you get back to your lab stations are 4 categories of chemicals. And on the lab papers, it says 10 chemicals are what you have to choose. I've kind of pulled it down to 6 because that's more achievable. You have to choose 1 chemical from each group, plus 2 more, of course. And you're going to submit to me your paper copy of your diagram. So go ahead and pull out a piece of paper. I want to tell you what you need to write down to help you Google navigate. So please put your phones away, because I don't think you need that right now. If you've not been paying attention, I hope your trick numbers will help you. Okay, so right at the top of your paper, MSDS. It's like SDS, but SDS means safety data sheets. That's kind of the new name. MSDS, material safety data sheets, are what they used to be called about 2 years ago. So most of the data on the web, you're going to find it's going to still have that name. So for example, if you want to look at sodium, and I already have that one pulled up, so I'm going to show you. Sodium. Here's what the SDS sheet looks like. All I Googled was MSDS sodium. Boom. Google Pro. Okay, don't put in, what's the safety information for sodium? Google wants quick and easy search links, right? So this is what it looks like. Kind of cool information, right? You're like, all right, so compatible or compositional information, nobody cares. Hazard information, this is about health. Maybe that's important to your safety symbols. Wink, wink. Okay, so that might be important. First aid measures, maybe information about your safety in terms of symbols, maybe not. The part about flammability might be pretty important, because do you think you should put something flammable next to something that is also flammable? Well, how do you, in a chemical storage room, maybe it's a room about this big, do you want to put something flammable here, 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 and here, or do you put them all together?
Yeah.
Why all together? So it's contained. So anything flammable, maybe it has like a own special compartment, versus like all just spread out. Like if you catch fire, well, guess what? This one, this one, this one, this one, and this one will catch fire. So think about that in your logic of how you would organize. You can also see what other things they react with, but I think the really most important or most helpful sections of these sheets are section 8 and 10. So it kind of gives you some information on storage, like don't breathe in the dust, right? Don't add in your water. So some of that's going to be important. Storage, what do you see here? Flammable materials should be stored in a separate safety storage cabinet. So I'm giving you a guide so that whenever you get back there, you're not confused. But oops, section 8. That's not the section I'm looking for. Section 10. They're pretty consistent on every single sheet, but sometimes they're a little different. So stability and reactivity. Is it stable? Yes. Is it reactive? Doesn't say it's corrosive. it says it's highly reactive with oxidizing agents, acids, and moisture, meaning water. So if you have other acids in your chemical storage, do you want to put this next to acids? No. So I'm just showing you how to read these. Does that help a little bit? Okay. So you guys are in groups of 3. Generally for the first lab group, like in the unit, I try to use my randomizer, which is frozen. Okay, I'll show you that in a second. Okay, this is your class. Nope, went too far. So you can see your lab groups are here, and I have 11 lab groups right now. So look for your name, and then let's see where we're going. So group 1 is at this, look behind me now, or behind you. Front lab station here. Group 2, and these are actually, they're labeled, used to be labeled on the side of the desk, but they're not. So 1, 2, 3, 4, 5 gets a big lab station right now. 6 and 7, 8 and 9, 10, and actually here's 11, who's my extra group. I'm going to have you you actually will probably share station 5 because it's big in the lab space, because it's kind of crowded right here, especially when your coaches are here. So please go to your lab station, and then I'll give you more instructions. If you sit at a lab station, stop your stuff under or kind of cover it if you possibly can. Let's see if I'll do those as soon as I can. You have me to the last step here for now. I just want to show you that you have a lab station. Alright, look at me, 5, 4, 3, 2, 1. Thank you. At your seats or your lab station, if you don't have a stool, you've been sitting all day, so that's okay. The pink sheets have exactly what I have on the board. Gives you a chance to kind of say, alright, Amaya, yeah, she's gonna look up the information on the chemicals she chose, and then so forth. The rest of her group, everything's right there. Right now, if you have a lab or a desktop like a computer, somebody can log on there. I do have the PCs. They take a little while to log on. So we do my group, and I'm gonna let you guys can grab this if you want to start researching online or on your phone. That's fine. But you have to use the same laptop every single time. That way, your members use it take forever to boot up every single time you use it. Make sense? Okay, so I'm also going to bring you around like a piece of purple paper. That's on what your final product on. Otherwise, you have another paper to kind of take notes on, and I'll take all of it at the end. Any questions? Thank you. All right, first group, guys, go look at the number on the top of the lab.
It all shot up onto the line.
You're gonna have to write down some of your research that's going to back. You're going to nitric acid and
When we're like sitting on the area,
nitric acid.
whether they're flammable, then we oh, if you're doing sodium,
No, I understand. I just think the big If your computer is slow as rocks, then grab your phone and use your phone for educational purposes.